All right, so I hope you guys are not too tired yet. We are going to continue with the InSAR pair processing with stripmapApp. So this is the first notebook I'm using ICE for data processing. And it's specifically about stripmap processing. That probably maybe Paul didn't have time to go through the details, but somewhere in his notes there are actually some notes on different SAR modes, and stripmap is one of those, which is probably the simplest. In this acquisition mode, we have the radar mounted on a platform, let's say an airplane or a satellite, and the beam is fixed in a specific direction. In a simple way, it could be just perpendicular to the platform direction, platform path. And it doesn't change through time while the platform is moving along the track. So that simple acquisition mode is called stripmap acquisition. You basically acquire a strip of scene while you are moving forward. Just to compare with TOPS, which is the operational mode on Sentinel-1, which you will hear about in the next few days, probably tomorrow. Stripmap is much simpler. Just from this figure, you can see that for TOPS you have the rotation of the beam along the track and also the rotation of the beam across the track to increase the swap. Basically, all these different modes have been designed for different purposes, specifically to go from stripmap first to ScanSAR was to increase the SWAT width. If you look at all data like NVSAT, ERS, or ALOS that we are looking at today, the SWAT width is smaller. It's around, let's say, 100 kilometers. But for many applications, you would like to, look at wider SWAT. So you have to do other modes. So this notebook and this ICE application is specifically about stripmap data processing, which was the traditional mode for most of the previous SAR modes. Even Sentinel-1 has a strip mode capability, but the operational mode is TOPS. So what does this application do? Just a very short summary. It focuses the raw data to a native Doppler geometry, and it can actually start from SLCs because some missions just provide the SLCs. And for interferometry processing, then you need to co-register the two SAR images. That co-registration in this application is done based on geometry first. So this works with most of the SAR platforms which have precise orbits. So don't expect it to work, for example, with RadarSat-1, but most of the other sensors, ERS, NVSAT, ALOS, Sentinel-1, CSK, TerraSAR-X, everything should actually work with this method. I'll go through a little bit more details what I mean by geometry co-registration while we go forward. And then the co-registration, which is basically aligning two SAR images on the same grid to do interferometry, might have some errors. So we can account for that error by cross-correlating the two images and find the misregistration. We get to very fine registration of the two SAR images. And this application, to my knowledge, was the first one, actually the first probably InSAR software that provided users with ionospheric phase estimation. And we will go to the details of that on Wednesday. By the way, if you want to follow me with this, if you want to run the notebook with me, I'll just show you where is it. On your server, notebooks, SAR training, English, UNAFCO InSAR, ICE2 docs. There is a folder, notebooks, and then navcode 2020, and then stripmap. And that would be the notebook that we are going to talk about today. At the top of the notebook, there is one flag that specifies if you want to use the stage data for this notebook, which means that we store the copy of the input data on S3 bucket, which is accessible only through OpenSAR Lab. So later, when you have eyes on your own computer outside OpenSAR Lab, then you really don't have access to S3 bucket. Then you should have that flag as false. In that case, the notebook will download the data from ASF. So the first cell is really just to set up your notebook and to look at the netrc file to extract the ASF user path, which is needed for downloading data. That's your Earth data logging information. So I'm going to just go ahead and run this first cell, which just
yeah, it failed for me too. Same problem.
That's
my netrc
okay.
File is there.
I believe that because few minutes ago it was fine, so I assume something with regard to the OpenSAR Lab changed.
Well, Franz was about to drop off, but now he's on. The netrc file is there for me.
Yeah, it's there. Strange. A few minutes ago it was working. It doesn't matter. I guess we will go forward. And while if there is any news on that, please update us, Paul. Is there anybody without getting this error? So is there anyone that has run this? Okay, so it looks like
fine.
Okay, so it looks like you guys are doing fine. Many of us on the system, so it could happen. Okay, most of the people are fine. That's good. So we will go forward. The next cell is really a function that, all right, thank you. No need to respond more. So I think almost everybody who responded looks like they got it to work. So the next cell is just to configuring the inputs. We will go to more details. This is just an automated function to write the inputs. So go ahead and run the next cell, which checks if the working directory exists or not. In my case, one of them did exist and the other one didn't, so it went through and made the data directory. The data that we are going to look at is over Hawaii. It's ALOS1 data over Hawaii, and that's the location of it. That's just for your information. Go ahead and run the next cell, which basically checks if the data is not there and downloads the data. And really, you don't need the .netrc file is not needed since we asked to use the stage data. So anyway, it should work. Even those who don't have the .netrc for today should be fine. So for me, downloaded the data to zip files. And if you ls, you should see actually those two files. Yes, it's there. And we unzip them. These are two ALOS1 raw data that we have downloaded from ASF, and this was a copy on the S3 bucket. And somewhere in this comment here, if we choose to download it from ASF, you can just simply download it with the wget command, but for that you would need the user path. So it unzipped. Inside one of the unzipped folders, you see that there are multiple files. And just a little bit more detail on what any of these letters mean, or group of characters, basically. For this specific case, when we say IMG HH, IMG HV, IMG represents image data, because we have LED, which is the leader files, where we have more metadata there. Some work report and some more probably internal processing files. But the most important one is the image data itself, the polarization of the data, which allows, and most sensors may come in different polarizations. In this case, we are looking at we have both HH and HV, but we are gonna process only the HH polarization. This stands for its ALOS pulsar data, and that's the absolute orbit number and the frame number. And the product level, the product may come in different levels. Raw data is level 0, for example, 10, what ASF has named. And the path of the orbit could be ascending, which is the path that the satellite is moving from south to north, or it could be descending from north to south. In this case, it's a descending orbit, as you see from this. We are right-looking radar, so this is a descending orbit. And if you look at the work report, just to get a little bit more detail, you'll see that there is the name of it, the acquisition time, and a few more details that you probably don't need all of them. In this specific case, I wanted to extract the acquisition date more automated in an automated way, and that's how we extracted the acquisition dates. We are making 2 directories, so let's run that cell. The 2 directories should be there, and we move the unzipped folders to those 2 directories, which we named based on the acquisition dates. Please don't worry too much about the netrc file right now. I would prefer you guys to go through the notebook with me. As far as you have the stage data as true, then you should be able to get the data from S3 bucket without netrc. We will be happy to solve your problem with your .netrc file. And if you have the latest version of the notebook, then it should, that's where you can find the notebook with S3 bucket. Before that, we didn't have it. So let's now change the directory to the process directory and make sure that where we are, yes, we are at the right place, Hawaii LS1. One more step before start processing the data is to prepare the DM, and in this case, again, we are going to download it from the S3 bucket, but I have already downloaded it, so it just tells me that the DM already exists. And finally, configuring the input files for ICE, specifically for stripmapApp to start processing. There was a function at the top of the notebook that for writing those XML files to the disk for you to be fed to ICE. Inside of those files are something like this. Basically, this cell configure inputs creates 3 files: reference, secondary, and stripmapApp.xml. XML files are the file format that we have for ICE2. Basically, the interface with ICE is through XML files mostly. And it's very simple to understand, I believe. For example, in the reference.xml, it says the image file is data in this directory which we created, and that folder that we moved to there, and that's the image file. So that's very clear. The leader file is the same thing, but LED is the leader file. That's where the the metadata is. For SAR processing, we have tons of metadata that we need for focusing the data and for basically geometry computations, orbit data, everything is there. And the output, because these are raw data and we want to focus them to SLC images, single look complex images, and they will be stored in this folder. Very similar to that XML, the other XML is the secondary .xml file, where we have the same, but note that the acquisition date is different, right? The first one, the reference date, we chose to be 2011 January 19. The secondary date is 2011 March 6. And then the final configuration file that was created is stripmapApp.xml, in which you tell ICE that this data that you are processing is ALOS. The reference, you could have the reference XML description here, but we made it simpler. We made a different file, so you could just look at the reference.xml. And secondary is at secondary.xml. And we have different unwrappers. In this case, we are telling the application to use ICU phase unwrapping method within ICE. There are many more configuration parameters at the end of this notebook. For example, what's the range looks, number of looks in range, number of looks in azimuth, the posting, do ionospheric phase estimation or not, many more that is in the end of this notebook, and you can definitely play with it. But this is the minimum parameters that you need to specify to start processing. And one example here is the DM, which in this specific example commented out. This is how you comment out in XML file. So basically this part will be ignored. If you don't want it to be ignored, you have to basically remove these parts, and it should be similar to what we have here. So we can go ahead and just take a look at first, before start running the different steps. Let's see what steps we have. And if you just say stripmapApp.py --help --steps, then you see a help description with different steps. And the first step is just startup, pre-process, crop roll. We will go through each step one by one, but it will give you a general overview what are the different steps that we are going to go through. So let's start with processing, and the first step, which is startup and pre-process. Go ahead and run that step if you want. It basically reads the raw data and extracts it, and it puts it in a format that ICE can understand. That's all it's doing. There is no specific really processing. It's just pre-processing and making the data ready for ICE to understand and to start processing in the next steps. Yeah, I see a question that says configure inputs. Yeah, you have to run that cell to have access to the function. So make sure that you start from the beginning. After this step, you should have a new folder called 2011-01-19 _raw, which you have multiple files there. The 2011-01-19.raw is basically your raw file. So these are the raw SAR data before even become SAR image. They are not focused yet. And the rest of the files are really just metadata. That XML is what we use for ICE internally as a file format to store our metadata, and the .vrt is a GDAL format, virtual raster table. It's probably Piyush has more. Well, actually, it was one of the pre-course notebooks about VRT files. And the next step is crop raw data. So let's say you have you want to process a subset of the data. You can specify that subset in your input XML file, which the instruction is in the end of this notebook. And actually, it's here too. You could have something like this, region of interest, and put south, north, west, east in this specific tag, and then we would crop the raw data. But we haven't specified any, so if you have to run every step, by the way, otherwise you will get error. So go ahead and run that step. I have already done it. And at the end of each step, it tells you some message, some meaningful message. You will see no region of interest provided, skipping cropping of raw data. We didn't really provide any region of interest, so we will go to the next step, which is forming the SLC. So go ahead and run the next step, which is form SLC. Basically, at this step, that's where one of the notebooks from Paul has a very nice and detailed explanation of what really happens during forming SLC. We have the raw data. You have to compress this raw data in range and in azimuth direction to get a single log complex image. I'll run this cell as well, and I suggest that you guys do the same. So it shouldn't take long, but what it's doing right now is probably doing the range compression first, compressing the data in range direction, and then it will do some range migration, start range migration correction, and then it will focus the data in azimuth direction, and that's when we have a single log complex image, stands for SLC. I'm going to check the messages here. Any questions so far? I hope most of you guys, yes, you can. All right.
So I was playing around and I restarted everything from the beginning. And when it got to the unzipping again, it actually asked me what I wanted to do, but there was no way, whether to overwrite or whatever. There was no way to actually do that. So I think you have to go into a terminal and delete. If you want to run things all the way over, you have to go in and delete the unzipped directories.
Oh, so you are saying that you had some zip files that were not properly downloaded? Is that the...
No, I ran through the cells following along with what you were doing, and then I wanted to cycle back and restart the whole process because of that netrc thing. So while you were talking, I went back and did that. And when it got to that step of unzipping the L1, the ALP, SRP, blah, blah, blah files, they were already unzipped there. So it asked me if I wanted to overwrite them.
Oh, I see. It was a Linux comment. Yes,
yeah, but I can't type it into the cell, so
yeah.
It just hang there. So if people do that, then you have to go into the terminal and delete those
Yes, that's true.
unzipped directories.
It's easy to go to the terminal. I assume you guys already know that. And by the way, whatever we are doing right now, it's in your, if you go to the terminal, it's in work Hawaii LS1. And for each step, there will be different files created there. And we started with the data directory, which were zip files, and that's what Paul is mentioning. And then we unzipped them, and they went to these subfolders. All right, so focusing the first SLC finished for me, and we can just take a look at that directory, what is inside, and you'll see that there is the data SLC, which is the actual focus image for data acquisition date, and there is the data SLC.vrc, which is just a GDAL VRT file, and the XML file, which is our ICE metadata file. Because of these VRT files, then our data are actually understandable by GDAL to some good extent, at least as of last year. And if you run it, it will tell you some useful information. For example, what's the size? 5,562 pixels and 27,648 lines. That's the total size of the data. And since it's not a geocoded data set, then don't interpret too much this part. It's still in radar coordinates, right? And we can actually open this file with GDAL and display it. For this is a very simple Python script to open the GDAL file. I know you guys probably looked at the notebooks from Piyush already, course, but it's useful probably just to remind. You can GDAL.open that file in a read-only format and choose a subset, and then read that as an array. Now you have a NumPy array. Since it's a complex image, then you can display the absolute part of it, which is the amplitude, basically, and the angle, which is the phase. And if you do that, you will see the displayed amplitude and phase. The amplitude probably makes a little bit more sense. On the left side of it, it's ocean, and the right side is land, which is part of the Hawaii, the Big Island. And on the right side of the see phase, which in this case is just random phase, because we are looking at the phase up on SLC. Yes, we haven't done any interferometry. And then the next step then would be crop SLC. We do cropping in 2 steps. We did have 1 step for cropping raw data, and then we refined that cropping to get to the actual cropping that the user asked for. Then the reason for that is, if you ask for a specific region of interest, we have to use more data than that to be able to focus to that region that you want. Then we do another cropping when we have focused the data. Since we didn't ask for any focusing, then you can run this step, but it will be just simply skipped. And then the next step will be verified DM. In this step, the application is going to check if you have specified any DM. It's going to read it and realize if it's a valid DM for ICE or not. If you haven't specified any DM, then it's going to go online and automatically download some DM, SRTM DM, not any, and use that for the region of interest. In this case, we use the already available DM on the S3 bucket. So you should see some similar message here. And the next step is run topo. Those who wanna run the notebook with me, go ahead and already run this step. And while I'll try to, this is the most time-consuming processing step for us, and we are already over time, so I'm not gonna let the notebook run. I have already done a pre-run. So while you guys go ahead and run your notebook, but I will try to explain what is happening in this step. So while your notebook is running for step topo, which the better name for it is really RDR to geo, which we mean radar to geo coordinates. All we have so far is our SLC image, which is in the radar coordinate system, and we have the orbit information. So we know where is our sensor at the specific time, and also at specific range, which is the starting range is given to us. We would like to know what's the position of the target that we have imaged. For each pixel of our radar image, of our SAR image, we want to do this computation. So to do that, we are relying on the modern sensors, not too new. Even NVSAT and ERS can be done with this method. The orbits are precise enough. Basically, centimeter level accuracy of the orbits are easily achievable these days. So we know the sensor position precisely, and we have the range, and we know which wavelengths we are looking at. That's the wavelength of our data, and we know the Doppler. And what we don't know is the target position, P. So by the way, here I am showing, this is the center of ellipsoids, in this case WGS 84. That's the ellipsoid surface. That's the position of the sensor, S, and that's the position of the target vector, P. From S to P is basically a range, or the distance from the magnitude of it will be the distance between our radar sensor to the target. And these equations are somewhere in Paul's notes. Probably you saw some version of it. What we are showing really is very basic radar equation, where the first one is just 2 times S minus P, which is the line of sight vector, dot product with the velocity. So 2 line of sight dot vector with velocity divided by lambda and R, which is the range, equals Doppler. That's a well-known equation. And the next equation is range, which is the magnitude of this vector from sensor to target position. And the last equation is just height of our point is going to be derived from an existing digital elevation model. So basically, the input here is not even the SAR image itself. It's just metadata. It's just what's the acquisition time at a specific pixel and and what's the range there, which we know. We are given those information, and the digital elevation model of the area that we are interested in, and we can solve with not very sophisticated methods to derive the target position. And these things can be really done precisely with the existing DMs like SRTM DM these days. So I assume this step will take some time. I think since I can imagine most of you guys in different time zones, so you might be tired, I will just move forward since I have a pre-run version of this, and you guys can continue processing and let me know either now or later if it fails anywhere. So after running this step, another directory is created called geometry. And inside geometry, you will see that you have lat.rdr.full. Lat stands for latitude, longitude, and Z stands for height. So the primary output of this computation is basically lat, long, height of each pixel of our SAR image. And those computations are done for the reference based on the metadata of the reference image. And if you want to take a look at what, and the LOS is the line of sight file, by the way, here. The line of sight is has two bands. One is the heading angle, and the other one is the incidence angle, from which you can always reconstruct your line of sight vector. And here the different extensions. RDR means that this is in radar coordinates. The grid is in radar coordinates, but for each cell of that grid, we have the latitude and longitude and height. And full just means that it's at the full SAR resolution. So each of these are rasters. We can do, can use GDAL and matplotlib to display them. And here is an image of a subset, basically, of these different parameters: latitude, longitude, and height. All right, so after this step, the next step is running. So the previous step was topo, or the better name, RDR to geo. Now we want to do the opposite. We want to start from this latitude, longitude, height from ground, which we computed based on the reference acquisition geometry, and get to the SAR coordinates in the secondary acquisition geometry. If you have finished the previous step, just go ahead and run the next step. This one is gonna be much faster, and while you guys probably are running different steps, I will just explain what it does actually. What is it doing is very similar to the previous step, but this time we are starting from the target position, which we computed in the previous step. So basically those lat, long, height are input to the next step. So for each of those, we are computing the sensor position. But remember, in the previous step, we were using the sensor position from the reference orbit. And now we are gonna use the secondary orbit. So we are starting from the target to get to the sensor. The equations are very similar to the previous equations. We need only these two. And the noun is target position, wavelength, and Doppler. And of course, the sensor is also noun. So that's where we are doing our iterations. And the unknown is the pixel location in the secondary image, the azimuth time and range. So that step also is completely geometry. There is no SAR image data itself there. It's all done based on the metadata. The main output of this step is actually the primary output is just the azimuth time and range. But then that's where we expect the data be. For that specific target, that's where we expect the SAR data for that pixel be. But that's not the case, right? So that's why we are doing all this. There is an offset, and that offset from just the difference of what we computed from the range and azimuth time, start range and start azimuth time will give us that offset. So basically, in result of this geometry computation, we get the offsets for the secondary image to map the secondary image to the coordinates of the reference image, because we cannot do interferometry between two SAR images that are not in the same coordinate system. And that's the process that we call co-registration. So that's the primary output of this step. We are going to look at it. So let me show you how does it look like. It's two data sets. The output is stored in directory called offsets, and we have azimuth.off and range.off. Again, they are rasters, so you can use GDAL and matplotlib to show them, to display them. We have the azimuth offsets here and the range offsets. So you see the azimuth offsets are varying a lot, between 12 to 30 pixels. The unit is pixels, and the range offset is around -2 to -1. This is for a subset. So what does it mean is, for each pixel, if for a given value here, for each pixel, that's the shift that is going to be applied to the secondary image to be mapped to the coordinate system of the reference image. Then you can imagine that the next step will be some sort of interpolation, because that mapping might not mean to get to the exact integer location of the reference image. So we need to do some interpolation, and that's what is called resampling. You can go ahead, if you have done all these steps, you can go ahead and run your next step, resampling. But before explaining resampling more details, I would like to mention one more thing, and that's one of the advantages of these geometry computations for doing interferometry and co-registration is we did two geometry computation. We started from the first orbit to the target, and we computed R1. And the second geometry was from target to the second orbit, and we computed R2. The difference of the two is delta R. And that delta R is exactly this equation you already saw around an hour ago from Paul's presentation, that that's the interferometric phase, 4 pi over lambda delta R. And since we have not used any image here, it's all metadata. So this is the geometry phase. This is the phase due to existing topography and the baseline separation in your scene. So this is great, because now we can just take out this phase from our interferogram if we want to use interferometry for getting to the displacement, which is probably the case for most of you guys here. So basically that's exactly what we are doing in ICE2 in this application. That we do those geometry computations, and we compute the geometry phase, which you might have heard in other literature, or today that it's topography phase or baseline phase. Or in even older literatures, you might see it as an interferogram flattening. And that's, believe me, most of my PhD was spent on understanding how the flattening was done on Roypack, for example. It was complicated compared to this simple equation. But with the precise orbits, it's really simple. So at the same time, while we are doing co-registration, we have the data to do the plotting of the interferograms too. And as I mentioned, since we have the offsets, then the next step is really do the interpolation to shift the secondary image to the coordinates of the reference image and do a resampling or an interpolation really. And we call it this step coarse resample. The reason for that is probably we just wanted to be conservative, that this resampling is using only metadata, only geometry, and there might be some residual offsets there. For example, due to delay in troposphere or ionosphere, or some older satellites, the timing could be not very precise. So we still call it coarse resampling, but it's not too coarse. It's still pretty good. So that should go fast, and after running the resampling, you have the co-registered SLC folder where you have coarse co-registered SLC, the .vrt files. Probably still don't have the refine. That's for the next step. But since I have already run that step, then you see that one there too. And now, similar to the previous SLCs that you have seen, you can just display it and just look at the amplitude. And as I said, so far, all we have done was just using geometry, using metadata, so there might be errors there for our co-registration. And the main source of error is, one, the orbit uncertainty in all cases. But actually, these days, now we are pretty confident that the main source is delay in troposphere and ionosphere. So we want to account for that delay and refine our offsets to sub-pixel accuracy. For interferometry, remember that you need to have the pixels at least 1/10 of a pixel. Usually, we aim for 1/100th of a pixel accuracy in registering the two SLC images. So you can run this step. At this step, what all it's doing is running AmpCore, or cross correlation of the amplitude images, between the reference image and the coarse co-registered image. So the two images are already, to some very good extent, maybe at sub-pixel level, they are already on the same grid. But now we are running amplitude cross correlation to find basically that sub-pixel misregistration. If you do that, then at the end, you will get to some misregistration, estimated misregistration in azimuth and in range directions. And in azimuth, it's around half a pixel. In range, it's 1 pixel, almost 0.98. It's almost 1 pixel, which is not small, by the way. One pixel is around 8-9 meters probably for LS1, so it's quite some shift there. Without doing this step, for this specific example, we wouldn't be able to get a good interferogram. So the result of this step is actually stored in a folder called misreg or misreg, and that just stands for misregistration. And it's in azimuth and in range, RG in range. And by now it should be, by the way, clear for you guys that range is, azimuth is along the satellite track, and range is across the satellite track. If you want to just open those misregistration files and take a look inside of those parameters that we estimated, it's also, there's a simple way to do it. And now that we have refined our offsets, let's do the interpolation again. Let's resample the secondary image to the reference coordinate system to get a better co-registered SLC. So that's what the refine resampling step is. It should go fast, this step usually. And after doing that, you will see that you have the coarse co-registered SLC and refined co-registered SLC. And there are some optional steps. In the previous step that we did for the refining the offsets, the misreg step, we were looking for only a constant offset for the entire image. The code is very, very flexible, and we could actually extract a polynomial also, but we don't want to complicate the processing right now, and we just ask for an offset. But in some cases, that might not be enough. Perhaps for C-band, X-band, that's more than enough, but for L-band, in some areas where Ionosphere is actually introducing extra shift to your InSAR images, then you have to do more for getting the co-registration done. And in that case, what we call is rubber sheeting. In that case, you need to turn on these options on, which is off by default, and do rubber sheeting, which means doing cross-correlation again, and this time not asking for only a constant over the entire image, but for an image of the offset derived from the cross-correlation. So that means that some more processing needs to be done. If you run it right now, it won't do anything because we haven't turned on those options in the configuration file. So go ahead and run that step if you are already there, and it will tell you just what's the next step, basically, which is forming the interferogram. All right, so we have two co-registered SLCs. The reference and secondary images are now on the same grid. We just need to cross-multiply them and get an interferogram. So the exciting part is getting close. And the result of this step is actually in the interferogram directory, topophase.amplitude, that's the amplitude of the interferogram probably, the correlation, dot full means it at the full resolution. Topophase.flat is the interferogram corrected for topographic phase. And that's what we want to take a look. But before taking a look at that, let's run the few more steps. The subband interferogram, that's what we will get back to on Wednesday when we are going to talk about Ionosphere. We are going to use the same data set. So run that step and then get to the filtering step. In this step, we are running the traditional Goldstein filter and the interferogram just to beat down noise a little bit more. The data is already multi-looked, which is averaged, but to improve the correlation. So at the end, you should see some interferogram like this one, and the left is just the magnitude. So what Paul showed you, you have in the theory section, we had two complex data, and you cross multiply, so there is a magnitude part of the input. The output is also complex, which has magnitude and phase. And now the magic happened, and this is the interferometric phase. This is part of the Hawaii Big Island, and the dark part is obviously ocean. Where you see the island, that's where the land is, obviously. The ocean is all noise, and the land has more ranges there. The coherence is high, the correlation. There are some interesting signals which are standing out. There is a long wavelength interferometric phase pattern here. Which we will get to it more on Wednesday. And then on the right side, in the middle, it was just a multi-looked interferometric phase. By multi-looking, it means that when we have the two SLCs, they are full resolution. We cross-multiply and we make an interferogram that is full resolution. Usually those interferograms are very noisy. And you average things. The complex domain, you just average over a window, And what you are looking at the middle is the phase of that averaged interferogram. That's what we say multi-looked interferogram. And on the right side, we have also applied a filter, which is called Goldstein filter. It's a traditional filter. You don't have to apply it always, but usually it reduces noise a little bit more. And if you look at just the subset of the interferogram, zoom in, you will see the signal, even here signal more. Basically, that's part of the active part of the volcano, probably the most active part here, which 2011, there was a dike opening. I'm not an expert on that, probably Garrett or Franz can explain more later if you guys are interested how to interpret this signal. But there is a very clear signal, geophysical signal here, which is due to the opening of the dike somewhere here in this volcano. So there are a few more optional steps for filtering the low band and high band interferogram. Don't worry about it. We will get back to that on Wednesday. That's related to the ionospheric phase estimation. And finally, the unwrapping step. Go ahead and run that step too. We are already there. And once it's done, we chose to use ICU because it's relatively a simple interferogram here, and correlation is high. ICU does a good job here, and it's much faster than SNAFU, but in most cases we have to use probably SNAFU. That's the default, but here we specified in the configuration file, we specified the unwrapper name to ICU. So once it's done, here's the output. That's the wrapped interferogram, which we looked at before. In the middle, it's the unwrapped interferogram. And if you look at the color scale, you see that the first one is minus pi to pi. And in the middle, it's from minus 15 to 15. So basically, those fringe discontinuities are gone now. Have integrated them the way that Paul briefly mentioned. And there is one interesting quality metric called connected component files that we strongly encourage users to look at. And just look how interesting that based on connected component, we could easily mask out the unreliable parts of the unwrapped interferogram. Because SNAFU or most of the unwrappers might give you answers even over ocean, but with this quality metric we call connected component, you can decide where is meaningful, where not. Basically, throw out whatever is zero. Connected component 0 means it's not reliable phase over there. So what has happened over the unwrapped area or during the phase unwrapping, here is just some 1D profiles of the wrapped, unwrapped, and what has been added. In this is 1D profile of the images that we just looked at. On the first panel, you see that the wrapped phase is around minus 1.5 to 2 radian. And during phase unwrapping, it has changed. The shape is exactly the same, but all has been added to it is one cycle actually has been subtracted from it. So the two in this specific case are the same, just because of the fringe, but overall fringe pattern, just 2 pi has been added, subtracted. More interesting part is this profile, where you look how phase is changing, gets to minus pi. It's a wrapped phase, so it cannot go more, jumps to pi. Minus pi, pi, and then again. But when we unwrap it, look at the scale that it's from minus 20 to around minus 5, you see that wherever that there was a jump, a 2 pi has been either added or subtracted. So that's what really is happening during the phase unwrapping. It's adding or subtracting the integer of 2 pi to the wrapped phase to get to this smooth unwrapped interferometric phase. The next step is Ionosphere, which is optional, and we will get back to it on Wednesday. But go ahead and run the last step, which is geocoding for today. And clearly, this step is gonna geocode the interferograms, and so far, whatever you have seen was in the radar coordinate system, in the range Doppler or range azimuth coordinate system. And now we want to just put it on a map coordinate system. And that will be the final result for the geocoded unwrapped interferogram. Basically the same image, but it's now on the meaningful map coordinate system. So that will be all. I encourage that all of you guys, please go ahead. That will be your homework to first. Everybody needs to really go through this notebook and get it to work and run it. So you saw how the results should look like. We will need the results of this notebook for the next session on Wednesday to talk about ionospheric phase. And if you want to know more about for example, those XML files, what's XML file, and different, some short explanation is here, and all different options that StripMapApp supports are also all explained here. Here we just by default used whatever range and azimuth looks that we compute on the fly based on the posting, which is default to 30 meters. So a lot of default parameters here. Filter strengths with default to 0.5. If you want to change it, go ahead and change it with a number between 0 and 1. Use high resolution DM. If you have it, give it high resolution DM. Do unwrapping with different, do unwrap turn on or off. Somebody just needs only a wrapped phase, so don't do unwrapping. Choose a different unwrapper name. Do rubber sheeting, which was the most precise co-registration that we can do. And do dense offsets. Some people just, for estimating offsets from large earthquakes or from glacier analysis for the offsets of the movements of the glaciers. So you can turn on the dense offset only. And parameters for offset parameters, the window size, the search window, the window height, you can set all those parameters and more and more. And if you want to process a different data set, you can process NVSATs, but the trick is that you have to change your reference.xml and secondary.xml using these instructions that we have at the end of the notebook for StripMap from Sentinel, LOS2, and many more sensors. And one more thing, that ICE is a library. It's not only StripMapApp or TOPS app, and you can do a lot more with it. You can have your own workflow, or you can contribute back your workflow. Here's very simple examples of how to use it as a Python library. You can import ICE, and you can import different modules and do your own parsing some metadata and do some computation with it. Two simple examples are here. Okay, I think that will be all for today. If there is any question, I know Piyush was actively answering questions on the chat.
So most of the people were probably paying more attention to the fact that Topo doesn't run, because everybody was given 32 threads and everybody was competing with each other. So hopefully people were listening to what Haresh was going through instead of just focusing on Topo not running. We need to fix that problem so that people can do the homework, I think, because if 80 people are trying to run it tonight, it may never finish for them either. So Franz is aware, and he's going to figure out if there's anything that can be done. I don't know, is there a way to like set OMP num threads in the script itself at the top and have that be?
Yes.
Okay.
Yeah, you can add after the exclamation mark OMP underscore num underscore threads equals 8, and then topsap blah blah. So it runs with 8 threads.
Yeah. So where would we? Right up there. Yeah. So bang. Export OMP. Will that work? Will that work? I think it's threads plural, right?
Yeah, so that won't save the environment. So in the exclamation call for topsap, you would have to do that.
Oh, for topsap. Yeah.
Yeah.
So something like that.
This is stripmapApp, of course, but
or stripmapApp, because environment, what you've done, environment does not get preserved for the next steps.
Yes, that's right.
So.
Okay, so for the students, where would that happen?
Wherever you call stripmapApp, say for the topo step.
So go to the topo step, and you say export OMP num threads equal 8 before you issue the stripmap command, or what?
Actually, can you go to the? I'm typing it into the thread.
That's plural, right? Num threads.
Yeah.
Okay, so you just precede the stripmapApp with the definition. Yeah. Okay. Okay. Yeah, that hopefully will fix it for everybody if everybody does that. So we need to make sure we get that message out. I think I'll send a group email out for because we only have 65 people on now, so at least 20 will not get it from the chat.
Okay, so great. The easiest, if they want to run through the whole thing without redoing everything, probably will be just to export in the terminal stripmapApp.py. You don't have to do really step by step. In your Hawaii LOS1, you just can do stripmapApp.xml --start startup --end equals end up. So this should go through everything. Or if you want to start from topo, you can just say from topo. But before that, you have to have OMP num threads as Piyush suggested. Calls to or something like that.